So, this is the official first day of the semester, last day, syllabus day, everyone's favorite day. But now we are moving on to the actual class because we got to get caught up with the other lecture, which is the in-person one. Because I don't think he takes, I don't think he does syllabus day. So we got to start off with chapter one. So chapter one was Chapter 1 is basically the introduction to thermodynamics. We're going to talk about some properties or some definitions, right? So the definitions are the basis for this class, and knowing the differences between them will help you in the long run greatly. So we're going to skip this first chapter, this first paragraph, because it doesn't really interest us very much. It just kind of tells you about what thermodynamics is. Essentially what thermodynamics is that it's the power of, it's basically heat and how in our class it's more or less the heat and how it is used for energy. And like, for example, how would you use like, how do you make power using, combustion? How do you make it using turbine blade, or spinning a turbine blade, things like that. So that's more or less the thermodynamic engineer part of the class. And so we have to start off here. So the first thing that we have to talk about is defining systems. So that's this right here with a really big line. So defining systems. So it says a system is whatever we want to study, right? So I hope that makes sense. Essentially, it's whatever we want to study. It may be as simple as a free body diagram or as complex as an entire chemical refinery. In our classes, they will be pretty straightforward, such as like a piston cylinder or something like that. They will never be a full chemical refinery, as said here, because that would be kind of crazy. But there are people that have gone to this university that have done a analysis of a full power plant. The one over by Lake of Egypt, a master's student, actually did a whole analysis of a power plant using thermodynamics. So he's pretty, and I think he actually now works he's the guy that runs the HVAC and energy of SIU. So his name is Justin Harrell. All right. So the system is basically whatever we want, right? So for example, if we're looking at a piston cylinder, the system is just the piston cylinder, right? It's just whatever is in front of you, whatever you are analyzing, right? And then it says everything external to the system can be considered part of the system's surroundings. So what that means is that outside of the system we are looking at, wherever you decide to draw that line. So for example, let's say the word system here is the system, right? You would draw your boundary as here. Everything outside of that circle is the surroundings, right? Does that make sense? And this will be in more practical terms whenever we start looking at questions, but essentially you just need to know the system is whatever we are solving, and outside of that is the surroundings. And then it says the system is distinguished from its surroundings by a specified boundary, which is essentially this line is the boundary. And you can draw this boundary however you want, although it makes sense in certain cases to draw in one place versus another one. So we'll get into although most of the times drawing the boundary is pretty straightforward, you kind of know where it needs to go, but it can be moved, and in other classes, it is actually important that you move it. So this is just you guys taking some definitions. If you want to write them down, you can, but this is recorded, so this will be posted online. So you can come back and watch it, but I would suggest writing a couple of things down, maybe on a Word document. All right. And then it says that you'll see that from interactions between a system and its surroundings, which takes place across the boundary, play an important role in engineering thermodynamics. That is true. Like, heat transfer flows across the boundary. Work can as well from an exterior source. So these are all things that we have to be comfortable with because, understanding heat transfer in and out and work coming into the system or exiting it is something that we need to take into consideration, because it affects how the numerical problems work themselves out. Okay? Alright, sorry. There's a message that came up. My apologies. Alright. So that says there are two basic kinds of systems are distinguished in this book. So we have a closed system, which is right here, and then we have control volumes. So a closed system is kind of how you would imagine it to be. It is essentially something that is enclosed. So think of if you have your water bottle with the cap on, that is a closed system. The system is what is inside the water bottle, right? And that's pretty straightforward. If you were analyzing the water as it heated up when it was closed, essentially that is a closed system, right? And a control volume is the opposite of that. So essentially mass is able to flow through it. So it's not just trapped with a cap, right? You can so think of a control volume as like your water faucet in your house. You turn the nozzle, or you turn the you turn the handle, water comes flowing out and then down, right? That is a control volume. It means that volume is being, or mass is being allowed to pass through the pipes as we go through the question, right? Or as we go through the system. It is not trapped. Does that make sense? I want you guys to type into the chat if it makes sense. I don't want to lose anyone. So, do say something. Sorry. Okay. So, and then, so now that we know that, it says the time, so then we can, there's like other ways to say it. So example, the term control mass is sometimes used in place of closed system. I've always heard it as a closed system. And the term open system is used with control volume. So think about it this way. If it is a closed system, it can be a controlled mass. Essentially, controlled mass means that you have controlled how much is inside of there, right? Like you have, 1 pound of water or something, right? It's not flowing and exiting. It's not changing. A control volume or an open system is where something can just change, right? So I usually see it as open system or control volume. Closed system, I only see of closed systems. I don't think I've ever actually seen control mass. So just think of those. All right. So we move down, down, down. These are examples of thermodynamics, like where you would see it in the world. So solar cell arrays, steam generators. This is an engine. Oh, that's biomedical. That's cool. And then this right here is how you fly your aircraft jet, right? So a lot of things. So refrigeration, that is one thing. That's a whole chapter in this class. All of these things. So in this class specifically, though, you will not solve things like this or this or this, right? Or even this. You'll solve parts of these. But in the next class, Thermo 2, you will actually solve full systems such as this and this, right? So this class is just doing it portions, right? Just to get you, your feet wet with the concepts and get your feet wet with how to solve properties, which we're about to talk about in a second. So essentially in this class, you'll be doing something like, we're going to solve only a compressor, right? Instead of the whole thing. All right. So then we have the system. So this is something you should definitely, once again, remember closed system as right here. This is a closed system. And this right here, if anyone recognizes it, this is a piston cylinder assembly in a car. It's attached to a shaft. So this is how your car actually functions, right? I'm sure there are some people in here that are motorheads and might know something like that. But yes, this is how it functions. It is a closed system. See? And then a control volume, which is the next one, which is where you can see right here, this is the control surface, the boundary of it. Air comes in, right? And then it exhausts out. So essentially the exhaust system is a bit different because you have air in and it's changing constantly, right? I gotta find the right thickness of that. All right. Let me see if this is important. Yeah, so this is important. So essentially, this is to tell you how to select your boundary layer. And the reason why this is important is because if you select the boundary layer poorly, you won't know what's coming in and out very effectively. And So that's sort of like where we're at, is that you need to always, this is probably a better example because they're using a dog and how it's like it's pooping. We don't really want to talk about that. Let's move to thermodynamics specifically. So right here, if you were to try and figure out, this is a storage tank, this is a compressor, air is being pulled in. This right here, this tank, if you were to, so this whole system, air is moving through it, right? But if you were to just do a closed system, you could say there is some air inside this tank, right? So that would be a closed system. But this right here, volume is being able to move across this boundary layer and into here. So they expanded the system to covering everything, which means that since air is allowed to flow across the boundary layer, it means that this is open. So that's how you should describe it, okay? So this right here, this isn't really that important. This is the important part though. So this is another big issue. So far what we have closed systems, open systems, right? And then now this is the next set of definitions that we have to get accustomed to, which is property, state, and process, okay? So let's talk with the first one. The first one is a property is a macroscopic characteristic of a system such as mass, volume, energy, pressure, and temperature, to which a numerical value can be assigned at a given time without knowledge of the previous history of the system. So this is a property. And so there are two types of properties which we will get into, but essentially what a property is, it's something about the fluid, something about what is going on inside. So for example, if you stick a temperature or a thermometer in water and you find that it's 80 degrees, that is a property of water, right? Would you agree with that? So I know this is all very basic, but yes, it is important that you get this because the next parts are a little bit different, get a little more in depth. So a property is something you can find about the system. It's related to the characteristics of the actual fluid or something. And then we have the word state, right? So state, in this instance, state is referred to as essentially, it's like a step in a process, right? So really quickly, that's the next one. But a state I think it as a step in a process. But I think what the book likes to refer to it as, essentially, it's it's something being described by its properties. So, for example, you could say that water over 212 degrees Fahrenheit, I think is the boiling point, turns into what? It turns into steam. So therefore, you could say its state is now gaseous, right? I think that's how they refer to it, and in this class that's very important because there are three states that we'll basically cover. We'll cover solid, the saturated, which is the middle part, and then boiling. So that is how I would think of it. I would think of it as essentially its characteristics are describing it. So if if water has turned to ice, it is solid, right? All right, so then right here, this is a process. And so what a process is, and their definition is, and when any of the properties of a system change, the state changes, and the system is said to have undergone a process. So for example, when you get to, let's say you have water. So let's say water, and this is liquid water, right? Liquid water, and this is state 1. If it moves to state 2, and now it is H2O, let's say gaseous, right? It means that something in here had to have happened to get it to be gaseous, right? And that something in here is most likely we added some heat, right? We added some heat into the system. So Q in this book is usually represented as heat. So we added something in, and that something must have been heat, right? Would you agree that if we have liquid water and it's now gas, some heat had to be put in? And so this right here would be called a process. From states 1 to 2, there was a process that took place there. Okay? It's a lot of information right now, but whenever we start doing questions, it'll make a lot more sense. I promise. If it already doesn't make sense, it probably does. It's hard knowing, really, because everyone's mic's muted, and I can't tell if anyone has any questions in real time. But that's okay. And then we have a steady state system. So right here, steady state. Steady state is as it sounds. Whenever none of the properties change with time, you are essentially at steady state. So for example, I don't know, I'm trying to think of like a really good example of this, but essentially if you think of like your room, and I know your room's temperature does stay steady with time, or doesn't stay steady with time. Actually, here's a good one. So ground temperature throughout the year. If you go, I think it's like 10 feet under the ground or something, it stays at like 55 degrees or something, just about all year round. And so you would call that temperature steady state. It is in steady state conditions because it does not change with time, right? So that is sort of what we're talking about. And the more important definition for this is that in a power plant, they usually use steady state conditions to describe how much power is being made every hour or something. So for example, obviously mass flow rate is going to change based on what is coming in, right? But you can't possibly know the variance and all that. So steady state conditions essentially mean that when something comes through the system, we just treat it as steady. Like we have this one amount of mass coming in, this one amount of power leaving. So it's something that helps us a lot, because if you didn't use steady state conditions, it would be very difficult to do a lot of analysis. You need to know a lot of other things. But in this class, steady state is basically always assumed. We always assume that we have the same things, although it usually says in the question, but we'll get to that. All right, and then earlier we had properties here, right? Properties. Now we have two different types of properties. So we have properties, and then we have extensive, and then we have intensive, right? So extensive and intensive properties. So an extensive property is essentially if its value for an overall system is the sum of its values for the parts into which the system is divided. So this is like, that was a really weird definition, but essentially mass, volume, energy, and several other properties introduced are extensive. Essentially, extensive properties depend on the size or extent of the system. So for example, mass depends on the size, right? So if you have if you have a 1 foot diameter circle like block of stone, mass depends on that. So for example, if that was now a 2 foot diameter block of stone, mass has changed. So it depends on the size, right? Volume the same way. And as you would probably imagine, intensive properties are not that way. They do not depend on the size of the system. And later on, there are more things that get introduced with this. So I think, what's a good one? I think entropy is one of them, if I recall. But we're going to get into those here in a little bit, more specifically all of them. But essentially, they do not depend on the size of the system. So extensive depends on the size of the system. Intensive does not. Hopefully that makes sense. Get rid of that before we roll onward. And then right here, this is a little example. We'll see how this is. So to illustrate the difference between extensive and intensive properties, consider an amount of matter that is uniform in temperature and imagine that it is composed of several parts. So right here. See? So this is dumbbells, right? Something that none of us have touched since the quarantine started. So the mass of the whole is the sum of the mass of its parts, right? And the overall volume is the sum of the volumes of the parts. However, the temperature of the whole is not the sum of the temperature of its parts. It is the same for each part. Mass and volume are extensive, but temperature is intensive. So essentially what they are saying is that mass and volume here, if you add it up, if you took this weight right here and you added it together, or you just put it on a scale, and then you took all of these weights and put them on a scale, they would equal the same, right? Would you agree? They would equal the same. But if you take the temperature of this plate or this plate, they may not be the same, right? They are separate from how big the system is, right? So that is the difference. That there are some properties that are separated from how big the system is or how much it weighs or what volume it takes up, right? And there's a reason why I'm harping on this is because it is extremely important that we get this. Because we're going to get into we're going to get into like finding table values, and you have to use those properties, extensive and intensive properties. So, all right. So then we have equilibrium. This is another concept. So equilibrium, essentially it's where, I'm sure you guys know what equilibrium is, but essentially it's where everything is zero. Opposite forces equal each other. Nothing is moving. We are in a steady, basically not changing condition, right? And then it says, let me see if this is there. Yeah, so this is, it's kind of something that I don't think it's not something that pops up a lot. But if something ever says that it's in equilibrium, it just means that we are at no changes, right? No changes were added to the system at all. It was isolated. How good are you guys with units? Like, for example, if I give you a kilogram, can you turn it to a pound? Okay, sure. There's probably a calculator somewhere for that, I'm sure. But yeah, with the conversion, I agree. You will have the conversion at all times. So I was just making sure because this next part just talks about units and has you convert units, and I don't really think I should spend a lot of time on that because I feel like you guys should know that by now. And if you don't, it's not that hard. So, easy. Yeah, easy. All right, so, but the units we'll be using in this class, so let me write those out. So, we'll be using something like kilograms, kilojoules per kilogram, which is an energy per mass, kilojoules per kilogram Kelvin, which is another one. And then you use the exact same thing, right? So it's pound mass, and it's BTUs per pound. These are the English equivalents, right? And then BTUs per pound Rankine. So these are the two set units that we'll pretty much use at all times. Obviously, the other ones like meters squared or meters cubed, feet cubed, inches cubed, things like that. But I mean, these are the ones that's specific to this class. You will see a lot of these types of units. And the first one is obviously mass. The second one is internal energy or enthalpy. And the last one is entropy. And we will talk about those concepts in the next chapter, which we will be getting to probably by the end of today, because we do have to catch up. But remember these units. This is the ones you will see mostly in this class. All right. So, and then obviously seconds and newtons and all that stuff, but we are beyond that. And then they talk about the English base. Here's some conversions they give you. We're not interested in that yet. Okay, so now we have an intensive property. So these are the important intensive properties that we are going to talk about. And the first one is specific volume, which is right here. Specific volume. So what this is it is the inverse of density. So for example, if you have the density of something, if you do the inverse of that, you get specific volume. So density is mass over volume, right? So mass over volume. Is that right? Mass over volume. I always flip them, but yeah, that basically one of them is specific volume. One of them is someone fact check me here just to make sure I have this exactly right. I always flip them. Anybody? I think it's this one is specific volume. Yeah, V over it. Because I remember, what's funny is because I've done so much of thermodynamics, I always remember specific volume way better than density. Because I know the units for this one, but never, I always forget that the other one is the other way. So this right here in this class, so this right here is density, right? Rho density. This right here is specific volume. And I know this is going to suck, but this is my specific volume is like a weird V. So it looks like that. So density, specific volume. In this class, we probably won't see density very often. So that goes away. This is the one that I want you to know, is that specific volume is something like that. V over M, which is in terms of like feet cubed over feet cubed per pound, or meters cubed per pound. I think that's the unit they use it in. Or not cubic meters per kilogram. Sorry, that's what it is. All right. And they just write this in terms of a limit, but like we don't need to know that. Essentially, it's just talking about like ratios of things, and that's not really important for us. All right. So then we have pressure. Everyone's hopefully heard of pressure, right? Essentially, it's just a force on an area, right? That is the definition of pressure, more or less. So pressure in this class, I'm sure you guys have all figured that out, right? Is that pressure is essentially just I'm sure okay, so you guys have probably seen pressure in like terms of like pumping a car's tires. What's another one? Like a pressure vessel, sort of like where you put your like propane, right? Things like that. A can of air that you guys shoot into your keyboards, or that I need to do. These are all pressure vessels to some extent. And essentially, pressure is just working at all points on there, right? It's just a force acting in all directions because of the pressure applied to it. Oh, I made that big. And this right here, once again, they represent it as a limit. But in this class, how pressure works in this class is that we use pressures to find different state points. So for example, if I told you like state 1 has a pressure of atmospheric, so like let's use this as an example, right? So if I said state 1 is here, you would go, oh, well, that means pressure 1 is 14.7 psi, right? Because that's atmospheric pressure, or 100 kilopascals, or 1 bar, right? You would say all of that. And then if I said state 2 is it here, with some other properties, you could find the pressure, right? So that's sort of how pressure is used in this class. It's used as a way to identify state points. So you remember those state points before processes before, like state 1 to 2 represents a process from 1 to 2. Those, how you fix state points is using pressure, temperature, specific volume, enthalpy, entropy, all the tricks in your bag is to use all of those things to try and fix state points so that you know everything about it. Alright? So more or less, it's kind of like a platform game in some way. Like, you're on state 1 down here. This is state 2. But before you can pass to get to state 2, you have to know everything here. You have to know all the stuff in between. You have to know it's everything about state 1 before you can move on. Alright. And then right here, we have pressure measurement. This one just talks about how like absolute pressure is, it's essentially this equation. But I don't think we've ever actually used this in this class. I'm 100% certain I've never seen this used. But it's just essentially it's the pressure equation where you know the balance of pressure is like total pressure is equal to like, atmospheric. And then this one right here I think is, has to do with what? This is, what is this? Oh, it's like liquid pressure. But I wouldn't worry too much about this. Our focus in this class is not to be doing things like this. You're going to be using tables with pressures already in them. So I wouldn't worry too much about something like this. It's not really that important. Buoyancy. Nothing in this class has to do with buoyancy, so we've never talked about it. And then we have pressure units. So right here, I told you I'm not going to spend much time on pressure, but in this class, what you will see is that in the back of the books, you'll be seeing things in terms of bar. Pardon me. You'll be seeing things in bars for the most part. And bars are 10 to the 5 Newton per meter squared. And 1 Pascal is 1 Newton per meter squared. 1 kilopascal is 10 to the 3rd Newton per meter squared. So they're related, right? So this is 100. So if you have 100 kilopascals, it equals 1 bar, right? So atmospheric pressure is 100, and I think it's 101 kilopascals, and atmospheric pressure is also 1 bar. So just make sure that's known. Oop. All right. So the next thing we have to talk about is temperature. So this is another intensive property, right? That I'm sure we all know. But I don't think we're going to spend too much time on that because I think we all understand temperature, right? I hope. And how to measure temperature. Thermometer or thermocouple. So, yeah, we're not going to spend too much time on that. It's not really important. And then right here, this is important though. So there are 2 scales that maybe you hadn't heard of before this. There's the Kelvin and Rankine scale. I don't know how far along you guys are in engineering to be in this class, but essentially, Kelvin is the SI version, and Rankine is the English version. So, for example, to get from Fahrenheit to Rankine, you have to add 440, I think. Pretty sure it's 440. Let me see. Oh, nope, 460. So Fahrenheit to Rankine, you add 460. So if you just take this and move to the other side. And then Celsius to Kelvin is add 273. So what this does, though, is this absolute temperatures. So if, for example, there are some fluids in this class that you cannot use Celsius for. It's for the ideal gas law. So you'll have to use absolute temperature, which is Kelvin, right? But for a lot of things, you'll be able to use Celsius. So basically, I would say this. For gases, you have to use Kelvin. For everything else, like all liquids, you have to use Celsius. Or Fahrenheit for liquid, Rankine for gas. So, but we'll talk about that more when we start actually looking at problems. I think that is pretty much it for this chapter. We want to move on to 2, but yeah, I think that's it. Mostly chapter 1 takes place in about 10 minutes for the main class, and then he moves on to 2. But I decided to take some time here just to be sure. So you're going to have to hold on to all those definitions because they're about to pop back up in Chapter 2. So Chapter 2 starts now. So energy and the first law of thermodynamics. So we have this is basically the first section that you would be tested on and the first section that you'll be getting homework over. So this is where the class really begins. All right. And so there's an integration here, so I don't know if anyone's really familiar with. This is something that I'm not really expecting anyone to know, but there's a derivation of the formula for energy, which is right here. So this is kinetic energy. So kinetic energy is the first type of energy, right? The other one is potential. So this is kinetic energy. Kinetic energy is like moving energy, right? So kinetic energy 1. So it's this right here. I'm sure you guys have seen this equation before, but essentially it's 1/2 times the mass times the velocity squared minus, or basically this is a change in energy, but essentially it breaks down into this. If you want the kinetic energy of state 2, it's this one right here. If you want the kinetic energy of state 1, it's this one over here multiplied in, right? But essentially, that this whole derivation gets you to that. It gets you to this is the kinetic energy, the change in kinetic energy. And if you recall, 1/2 mv squared is in the kinematic equations, right? That you might do in like dynamics or something. It's also in there. And then we have potential energy. So in this class, potential energy is almost always neglected because it's really potential energy is just a function of how high you are up and how much mass there is, right? Which is this derivation as well. So if you see potential energy is this is PE, it is mass times gravity, and Z's in this class. So this Z concept right here is the height. So essentially, potential energy is just a function of mass times gravity times the difference in height, right? So the reason why this is often neglected is because potential energy usually you have to be up some massive amount of height for it to be like a super huge. So generally speaking, so like for example, what's the potential energy difference of like something that's on the ground versus 5 feet in the air, right? I mean it's not massive. So the reason, and most of the time, in a lot of these power plants, most things take place on like the same level, but then they get transferred down to another level, and then they be on the same level again. So potential energy is usually negated. Now there are some power plants that potential energy is how they make power. So for example, like hydroelectric. There is a lot of times potential energy is how they make power. It runs down a mountain and then it spins a turbine and then they pump it back up. So there are some that use this potential energy as a concept to making power, but in our class it gets negated a lot. It doesn't actually count for us. And they will probably say this in the problem. It'll say potential energy effects have been negated or are negligible. So. And then we have units for energy. So as I said earlier, for SI units, you have kilojoules right here, right? And for English units, it's probably your first time seeing it, but it is BTU, which is a British thermal unit. So kilojoules, BTUs. You'll see both of these as the class rolls on. And this is just like a simple conversion right here, or not a simple conversion. This is just to show you how much energy. So right here, as you can see, essentially if you drop this, so where'd they have it? It had 10 meters high, right? So they had it 10 meters high, a mass of 1 kilogram. You got 10 kilojoules as an energy off of it. So as you can see, the values of the energy are fairly low, unless your mass is really high. And your differences in height are really high. So that's why they're often neglected. I mean, 10 meters up is decent fall. Alright. And then we have conservation of energy in mechanics. So, conservation of energy. I don't know if anyone has ever heard of this I don't know, it's not a property, but essentially this law of conservation of energy. So, the law of conservation of energy means that essentially all of the energies have to add up to be zero, right? Because if it's not kinetic, and if it's not potential, if it's not leaving as heat transfer, if it's not leaving as work, they all have to be equal to each other, right? Because you don't just lose energy, right? Because what is it? Energy is neither created nor destroyed, right? Sort of thing. So essentially, it has to leave as something. Whatever that is, it is something. And so that's the reason why you can use this principle, is that all of these have to be equal to zero. The kinetic and potential energy must be equal to zero, right? And so that's what they've done here. So what this says right here is that the kinetic and potential energy of state 1, so let me do that. The kinetic and potential energy of state 2 equal the kinetic and potential energy of state 1. So energy has been conserved for this equation, right? And what it says here is that the equation illustrates that energy can be converted from one form to another. For an object falling under the influence of gravity only, the potential energy would decrease as the kinetic energy increases by an equal amount. So that is a process. That is a concept that we have to think about right now. And then there's another one called the law of conservation of mass. And what that one means is pretty simple: is that if you put in, like right here, if, let's say that this right here is a water faucet or something, or a simple heat exchanger. If you have 1 kilogram going this way, and then you have 2 kilograms coming down here, the exit, their addition has to be equal to 3 kilograms, right? So conservation of mass means that mass is not leaving this system in any way. It's conserved. So that's what that one is, and they'll talk about that one in a minute. All right, and so now we have to talk about work as a definition. So work is equal to the integral of f ds. So that is once again another integral. I try to deal with things not in the most difficult terms, but this book has an interesting take on what work is, so it is right here. And by the way, this will probably be a question on your exam or a question on your homework, so I'd pay attention. So it says, the thermodynamic definition of work. Work is done by a system on its surroundings if the sole effect on everything external to the system could have been the raising of a weight. So I know that sounds really strange, and it did to me as well. But essentially what it is saying is that work is only done by a system if the sole effect, the only effect on everything outside the system, is that it raised a weight. So I know this is the thermodynamic definition of work for this book, so I would hold on to that in a second. So just hold on to it. And then it says, notice that the raising of a weight is in effect a force acting through a distance. So the concept of work in thermodynamics is a natural extension of the concept of work in mechanics. However, the test of whether a work interaction has taken place is not that the elevation of the weight has actually taken place, or that the force has actually acted through a distance, but the sole effect could have been an increase in the elevation of a weight. So, really quickly, now this is an example, so we're going to talk about an example. Once again, hold on to that definition. It's really confusing. This will hopefully clear it up for you. So we have an example here. Right here is the example. It says, consider this figure right here, showing 2 systems labeled A and B. In system A, gas is stirred by a paddle wheel. So right here, you can see there's gas inside this chamber, and a paddle wheel is stirring it, right? It's increasing its energy. It says, the paddle wheel does work on the gas. Would you guys agree that as this thing turns, it is essentially given work. It is spinning and it is giving energy over to the gas in terms of its work spinning, right? Essentially, it's a transfer of energy. All right, and then it says, in principle, the work could be evaluated in terms of the forces and motions at the boundary between the paddle wheel and the gas. Such an evaluation of work is consistent with the previous equation. Someone had a question and was typing in. Who was that? You caught the corner of my eye as I was reading. Mr. Tanner. Sorry, no problems. Okay. And then it says, so contrast this system with the other one. So it says, consider system B, which is this one, which includes only the battery. At the boundary of the system B, forces and motions are not evident. Rather, there is an electric current I driven by an electric potential difference existing across the terminals A and B. That is the type of interaction at the boundary, this type of interaction at the boundary can be classified as work follows from the thermodynamic definition of work previously given. We can imagine that the current is supplied to a hypothetical electric motor that lifts a weight to its surroundings. So it says, work is a means for transferring energy. Accordingly, the term work does not refer to what is being transferred between systems or what to do or to what is stored within systems. Energy is transferred and stored when work is done. Okay? So real quick, that work in this class is going to be fairly obvious a lot of times. So for example, if you see like a paddle wheel spinning, you guys can obviously agree that if this thing is spinning, something had to be supplying the energy for it to spin. It doesn't just spin on its own, right? So that means that this is doing the work. So, and then we'll get into other ones as well. So sign convention and notation. So really quickly, work done by the system, which means that this is positive work, which means so for example, this is work leaving a system. So whenever you guys get your power from a power plant, that is positive work. It is leaving the system. We generated it, right? We didn't take in work. Like a power plant doesn't cost more power than it produces, right? Or else it wouldn't be a power plant. So really quickly, work done by the system is positive. Work done on the system is negative. So if you have to put in work to something, if you have to put in work for something to happen, that work is negative. If you are getting work out, it is positive. So remember these things right here. So really quick, so this is positive, this is negative. Okay? And this is pretty important when it comes to the sign convention for work. Heat transfer is the exact opposite of this. So when we talk about heat transfer, which will probably be next, that'll be what we get into. And then it says work is not a property of the system or the surroundings. In addition, the limits of the integral of equation 2.2 mean from state 1 to state 2 and cannot be interpreted as values of work at these states. The notation, or the notion of work, at a state has no meaning, so the value of this integral should never be indicated as W2 minus W1. So basically they're just telling you what not to do there. So let me get rid of that, and I think really quickly, let me see if we should stop here before we go. Where's heat transfer start at? Huh. Okay. I was wondering where heat transfer started. So it is 48 after. And I think we are probably going to stop for right now. So let me see. 2-1 and 2-2. So we are on the right track so far. So we will come back on Friday and we will finish 2-3 and 2-4, which is essentially the next part of this chapter. And I will upload this PowerPoint as soon as I can. Or not PowerPoint, but I'll upload this video as soon as I can. And I'm going to take attendance right now as well. So I'm going to stop this and we can take attendance.